Thank you, everybody, and I'll try to make this quick. This is a presentation about the UHPC repair of steel columns in the Walnut Tunnel. I am not a student or a recent graduate, but we're all students of life. So since yesterday's sessions were full, Kai graciously gave time today. I'm hearing some background talk. I don't know if somebody needs to mute their computer. That would be nice. Oh, I think it's our former speaker. I don't know if you're able to mute him, Kai. Anyway, I'll power on. So as I said, I'm not a student or recent graduate. I have 24 years of experience in design of bridges, a lot of experience in UHPC, and about a little over a year ago, I joined Steelike as their VP of engineering. Normally, I'd be co-presenting with Joe Serignano from Benesch Corporation. He could not be here today, but he is the VP and structural group manager of Benesch in the Lehigh Valley, Pennsylvania division, and his team was responsible for the design of this project. So I'm going to do a quick overview of the project, discuss why UHPC was selected, and then talk about the construction and then give some conclusions. So the Walnut Tunnel, it's owned by PennDOT, Pennsylvania Department of Transportation, but it goes over a SEPTA facility, Southeastern Pennsylvania Transportation Authority, which runs a lot of the mass transit around the Philadelphia area. This structure was built in 1955. It's a tunnel, but it's really just a bridge over a cut, so a cut and cover tunnel, if you will. It's a multi-span structure, but the primary direction of the beams is transverse, as you can see in the sketch in the bottom right. The west side is supported on an old masonry wall. The right side is supported on reinforced concrete. Sorry, this is the masonry wall here, if you're seeing my pointer. Let's see if I can do a better job of that here. This is a masonry wall, and then we have a steel column support here, and this is a reinforced concrete abutment wall. So the scope of the project involved replacing the expansion joints, which you can see in this photo here, as well as concrete deck repairs and critical steel repairs inside the tunnel. This $15.6 million project, which was awarded to AP Construction. So one of the challenges with this project is that the rail line in the tunnel is an active rail line, and it's the regional airport rail, so it's a rather important rail line. And the project planning allowed for a 3-week outage using busing as a substitute route. Somewhat fortunate for the project, though, the COVID pandemic during the course of this project resulted in a sharp drop in ridership, so the project owner extended the outage to 7 weeks. So the project was based on the PennDOT standard special provision for UHPC with a couple additional criteria. Specifically, it required a minimum compressive strength of 12 KSI in only 12 hours using accelerated heat curing. And the goal was to ultimately provide additional compressive and buckling resistance to the steel columns that were experiencing significant section loss, and then of course protect those columns against future corrosion in the tunnel environment. And in these photos, you can see some of the, these are the exposed steel base plates. You can see some signs of corrosion here. Here's some other corrosion inside the tunnel. And on the right, it's just a general layout. And this is the row of steel columns that were repaired using UHPC. And you can see there's essentially a crash strut that connects most of those. And the masonry abutment is behind it. So because of the extended tunnel shutdown that was allowed due to COVID, the owner ultimately relaxed the 12 KSI and 12-hour requirement. So it was no longer required to heat and do an accelerated cure. So the criteria was relaxed to a standard cure rate. So this is the basic detail. On the left is the existing condition, showing the existing concrete encasement of the steel pedestal, and that encasement was removed. And on the right is the UHPC repair. So not only was the steel pedestal encased in concrete, encased in UHPC now, but that encasement was extended up to the bottom of the crash strut or collision strut, encapsulating all of the section loss. So now we'll move into construction. Of course, the first step was to excavate, remove concrete, and then install formwork. What you see here is the lower half of the formwork surrounding the steel section, or the steel base assemblies. And now we have the formwork with the second stage extending up to the collision strut. The total assembly was about 7 feet high from the existing footing, which you can see it on the right side of the bottom. Just to help give a sense of scale, right here is Bill Coolish, Steelike's CEO and the inventor of Steelike UHPC, posing for a photograph. So once the formwork was in place, the next step was to, of course, mix the UHPC. The UHPC was mixed in a standard, in this case, front loading ready mix truck above the tunnel and away from the work area. So you can see here, super sacks of dry mix are being loaded into the drum of the ready mix truck. Now water is being added. And finally, steel fibers are being added. And you can see in this photo, you can see in the background, this is, nope, I'm sorry, that's not the work area. We're looking the opposite direction. That's the 30th Street station you see in the background there. So mixing in ready mix trucks created a number of advantages to the project. First of all, large batch sizes, up to 6 cubic yards were mixed per batch. In fact, up to 7 cubic yards is possible. So mixing large batches was possible and allowed the mix to stay alive for a long time because of the low energy nature of mixing in a ready mix truck. In fact, there were cases where there were form leaks during discharge. So discharge had to be stopped and the mix had to remain in the ready mix truck for an hour and a half or more. And this was, even though it was done at nighttime, it was in 80-degree temperatures in August. So once the UHPC was mixed, it was time to place it in the forms. What you see here is a telehandler lifting a concrete tremie about 70 feet long, which will then be inserted into the open deck joints and drop down into the tunnel below. Here it is being lowered down. Finally, it's in position for discharge of the UHPC into that funnel at the top of the tremie. And now you can see the tremie line extending down into the tunnel along the column line. This was a 6-inch tremie line. At the bottom, the contractor used a 4-inch reducer. The repairs were only 30 feet below the deck, but because there were limited openings in the deck above, the tremie had to be up to 70 feet long in order to move laterally to hit all of the column forms. Yeah. So once the tremie was in place, the ready mix truck simply drove up to the tremie line, extended the chute, and started to discharge into the funnel at the top of the tremie. So this created more advantages to using the ready mix truck. First of all, the UHPC was mixed outside the tunnel, above and away from the construction area, so eliminating congestion in the tunnel. And the truck simply drove right up and discharged into the tremie. This method saved time. It also reduced waste versus using buggies to move the UHPC from the stationary mixers to the repair location. In addition, each column repair form consumed 1.5 cubic yards of UHPC on average. So the large batch sizes, therefore, were able to provide a continuous flow of UHPC to fill up to 4 column repair forms per batch. So with 50 total column repairs to be done, those were filled in about 13 batches. Now, if you were to use more conventional, either the 0.6 cubic yard pan mixers or the 1.4 cubic yard horizontal shaft high shear mixers, you'd be looking at 58 to 116 batches. So the ready mix truck mixing really simplified things here. And as I mentioned before, a couple of times the contractor had to stop discharge in mid-batch due to form leaks. And in fact, as I say here on the slide, Steelike was able to keep the UHPC remaining in the truck alive for more than 2.5 hours in very warm temperatures. So as I said, the 12 KSI and 12-hour limitation or requirement was relaxed. So we just went with standard curing. And you can see here, with the exception of one set of data that lagged a little bit, everything met the project criteria of 21.7 KSI strength in 28 days. So here's some photos of the completed repairs. On the left, you're still seeing the formwork around the lower portion of the repair that surrounded the steel base plate or steel base assembly. On the right, those forms are now removed and the backfilling has already begun, or it may be completed in that photo. And here's a overview of a number of the completed repairs, fully backfill, and the gravel is brought up to the final grade. So a couple of conclusions here. This was, as far as I'm aware, the first use of UHPC for steel column repair in North America, at least in the transportation sector. Due to site constraints for delivery of material, the use of UHPC facilitated rapid placement over the active regional rail facility. UHPC does provide long-lasting protection against future corrosion due to its extremely low permeability. Steelike UHPC flowed easily through the 6-inch tremie and 4-inch reducer, allowing all UHPC mixing and discharge to take place outside the tunnel. And mixing Steelike UHPC in standard ready-mix trucks provided numerous advantages that help accelerate the placement of UHPC and reduce waste. And the unique properties of Steelike UHPC provided the contractor with lots of time flexibility when formwork problems arose without having to waste any UHPC, all in hot weather.